The objective today is to explain in broad terms what makes a key difficult to crack. So a really fun lesson and a challenge at the end of the lesson, all relating to encryption and decryption. In this lesson, students learn about the relationships between cryptographic keys and passwords. Students explore the Visionaire Cipher with a widget to examine how a cryptographic key can be used to encrypt and decrypt a message. Then students use a tool that shows them about how long it would take to crack a given password using a standard desktop computer. Students experiment with what makes a good password and answer questions about the human components of cybersecurity. So as we get into this lesson about combinations of letters that make up passwords, I just want to quickly review what permutation means and the difference between permutations with repetition and permutations without it. I'm not going to read this whole screen, but basically if you have a group of numbers or place values where permutations are repeating, well, essentially this is exponents. If you have n different types and n choices each time, like after you've chosen something, it doesn't just disappear, well then that's when you use exponents. Essentially here they're saying you have a number to the r, and the r is the times that that number can be chosen. So here's the example. If you have a lock and there are 10 numbers to choose from, 0 through 9, and we choose 3 of them, the possible permutations that exist is 1,000. So a simple lock, they're incorrectly called combination lock, like in the lockers in the hallway, or if you have a lock for your gym locker. If you have 3 choices and there's only 0 through 10, so I'm talking about a smaller lock than you're probably used to seeing, even when it's that small, 0 to 9, there are 1,000 possibilities to try. Now, if we're talking about something where once you've chosen the number, it just disappears, well, this is where we're talking about permutations without repetition. And this is my favorite example, the pool balls example, where every time you've chosen one, that number needs to be taken away. So you reduce the number of available choices each time. So let's say after choosing, say, the number 14, we can't choose it again. And even if we didn't want to put all the pool balls in order, maybe just 3 of them, well then the number is still being reduced, just not as much. So if I have 16 pool balls and I'm going to choose 3 of them and put those 3 in some sort of order. Well, once I've made one choice, now I only have 15 other choices, and then at making another choice, I'm down to 14. So essentially I have 3,360 possible orderings that I can do. So with that said, the Visionaire Cipher, put simply, is just a byte-wise Caesar cipher. That means every character in the plain text is shifted according to every character in the key. So if the key is of length n, then the ciphertext is going to have 26 to the n possibilities. So here, if you could tell me what the Visionaire Cipher is, that'd be great. The picture is essentially saying encrypt the message, make it happen using the Visionaire Cipher and the keyword math. So start with the key. The keyword math, M right here is 12, and then you see A is 0, T is 19, H is 7. So if I'm encrypting make it happen with the keyword math, this first M is going to be moved over by 12 spaces. So M will go down to Y, and then A will go down to nothing. It would be A. K would move over 19 spaces, which is pretty far down the line, so you see the pattern I'm going with here, right? Now recovering the plain text from its is impossible because you got to check each and every character without a key until some reasonable messages come out of it. But what's a reasonable message? So while shifting WNBUQ, okay, according to cats, returns unicorns. So I'm using cats as the key on this Visionaire cipher text After using the numbers that come from cats in order here, I can come up with the word unicorns. Now, there should be a lot of other keys out there other than cats that could return something that's reasonable. And for instance, if I use the key, this jumbled mess of a key to decrypt, I could get the word mermaids. So mermaids is a word, so is unicorns, depending on what I'm going for here. I would specifically need to know what that key was. You know what I'm saying? What the specific key is. Not just maybe any key, but a specific one, like cats. And then think about, from a bad guy's point of view, what's easier to guess, the word cats or this jumbled up mess? Think about how many permutations exist when you have a 4-letter password versus more letters. And notice the pattern here. The key does not have to be as long as the thing that you're encrypting. So 1, 2, 3, 4, 5, 6, 7, 8 letters here, 8 letters here, and then 8 letters here, even though this was only a 4-lettered key. So the Visionaire Cipher uses all 256 ASCII characters instead of the 26 letters of the English alphabet. This leads to 256 to the n possibilities. While this scheme ultimately renders the brute forcing thing impossible, it's still crackable. And I will show you that in my challenge here. I'm going to ask you to try to guess my password, or guess a password, not the one I always use. I've made a ridiculously easy password as a key, and if you can guess it, there will be a reward. I'll talk about that in just a second. For now, if you'd like to learn more about this, there's a great blog about the Visionaire Cipher right here at the link of wafflescrazypeanut.wordpress.com. So let me wrap up some information here about encryption, and then you'll get to practice yourself. Strong encryption techniques are typically publicly known algorithms, but have mathematical properties which ensure that the original message cannot easily be retrieved. Essentially what that paragraph is saying is that some math magic happens, and that's how we make computers work, or at least make encryption work. These techniques typically feature a secret key or piece of information that is used when encrypting the message. While the algorithm can be publicly known, the secret key is not. The art of encryption is coming up with an algorithm that, 1, makes the message undecipherable without the key, and 2, is such that the key should only be discoverable through an exhaustive search of all possible keys, rather than through some analytic technique. Your think, write, share here is what are 2 things that an encryption algorithm needs to do. Now here are some reasons people might try to crack a cipher. The first one is people in the field of counterterrorism make a living by trying to crack the codes of other nations. Many attribute the success of the Allies in World War II to our ability to crack the Enigma code and uncover the plans of the Germans. There's a really good movie about that, actually. The second reason might be others are trying to crack abstract codes that are not written by humans. Searching for patterns within DNA models is an example. Not just the idea that maybe there are codes coming from aliens in deep space. I really like that DNA model example. So abstract codes would be the second reason. Another reason is just plain fun. So it's useful to try to crack your own codes to see how strong they are. And the fourth one, which is sort of a jumble of many more, it just says there are many reasons related to mathematical exploration, pattern recognition, etc. So my think, write, share here is of the 4 reasons, which one would you be most interested in learning more about? So we're using a lot of big words today. Algorithm here on the Big Bang Theory, Sheldon had talked about a friend algorithm, I believe it was, and we're talking about the word encryption, that's a big one, and then cipher now, and the Visionaire Cipher. There's a common misconception that cracking and decrypting are interchangeable terms, so let's just get our terms right. Decrypting is just using an algorithm to undo the encryption. It's like using a key to unlock a lock. It's what the sender is expecting the intended recipient to do to recover the original message. Cracking is more like detective work. It's like trying to pick a lock, using various methods to try to figure out what the secret message is without having or knowing the decryption key ahead of time. So my think, write, share here is, in your own words, what is the difference between cracking and decrypting, and which one is more interesting to you? Today we'll attempt to crack codes, paying particular attention to the processes and algorithms that we use to do so. Before starting, we want to make sure that we can distinguish between an encryption algorithm and an encryption key. An encryption algorithm is some method of doing encryption. The key is a specific input that dictates how to apply the method and can also be used to decrypt the message. Some people might say, what is the key to unlocking this message? Your Think Right Share, what type of input do you need to apply the algorithmic method of encryption? If you need help here with the sentence starter, the type of input you would need is called a what? So to dig in a little deeper here, here's an example. The Visionaire Cipher is an encryption algorithm that involves shifting the alphabet. The amount of alphabetic shift used to encode the message is the key. When you're cracking the Visionaire Cipher, you are trying to figure out how much the alphabet was shifted. You are trying to discover the key. Perhaps counterintuitively, publicly known encryption algorithms are often more secure, since they have been exposed to a much more rigorous review by the computer science community. Making an encryption algorithm public allows computer scientists to verify the security of the technique either through mathematical proofs or by trying to crack it themselves. Your Think Right Share here is contrary to what most people may believe. Why is making encryption algorithm public a helpful thing to do? We've just recently figured out the SHA-1 algorithm is a no-go because there are some conflicts, and there's more details I want to tell you about that, but we've got to stay on topic here. The objective is to explain in broad terms what makes a key difficult to crack, so we got to get to cracking here. There's a difference between the algorithm, that is how to execute the encryption and decryption, and the key. So in encryption, you should always assume that your enemy knows the encryption algorithm and has access to the same tools that you do. What makes encryption really strong is making it hard to guess or crack the key, even if the enemy knows the encryption technique you're using. Think Right Share, why doesn't it matter if the enemy knows the encryption algorithm? I know this question is similar to the last one, but try to take it a little differently. Here's a sentence starter if you get stuck. Knowing the algorithm doesn't matter because... So time to get cracking here. I want you to play around with this widget first, and then I'll give you a little more direction soon. If you absolutely need a starting point, so here's something for you to just think about. I want you to encrypt a few different messages using different keys, then decrypt the message. Try to find a bad key, try to find a good key. Try to decrypt without knowing the key. But right after I give you the link, I'll provide those questions so you can pause and play this video at your own pace. So here's the link you're going to. For those who are actually in the class, I've pasted this on Canvas. Here we are at the actual link, and so it says here, enter your text message. I typed this, then enter a secret key, so I just came up with something random. Then to encrypt, I could push play, and I could watch how that Visionaire Cipher begins to encrypt. Scroll down a little. Here's the plain text, here's the ciphertext that it's generating. And then when you run out of patience, you can just click like fast forward here. And this is the ciphertext, the meaningless jumble of letters that could be sent across the airwaves or sent across the wire. And the bad guys would never know what this means unless they know the key, because then they would go here and type in the key and watch the process go backwards. So then you can take this, I'm going to copy, I'll put it up here, and then I can delete the key, and then I can try something random. First I said cheeseburgers, let's say here I say tacos, so then I'm going to click decrypt. I'm going to take this ciphertext and try to figure out what it means. So here I go and I'll push play. Alright, so the plain text is coming out all jumbled and meaningless, right? Let's pause. I'll go back to cheeseburgers. Oh, not capital. Cheeseburgers? I think that's how I spelled it. I hope. Okay, so see, it's working. I had the right key. So at the end of the day, there's really no cracking this unless you are a computer, or unless you do some social engineering, which I'm going to ask you to do here in a moment. I want you to take a ciphertext that I'm going to provide, paste it into here, and come up with a couple of things you think I might have typed as a secret key, aka a password. So try a couple. Cats are awesome. Try a couple different things you think I could use as a password, and let's see who could be the first one to discover my message. Right here is my ciphertext for you. What I'm saying, whoever can tell me the secret message first, it can only be one, maybe two, if you guys want to work in partners. But whoever can tell me my secret message first, I'll buy you lunch. You have 24 hours to figure it out, so if you don't do it in class, that's okay. I'll check in with you the next day. And for those who are in my class, I'm going to paste this. That way you could just copy and paste and make sure you don't mess up any of these letters here. Okay, so let's take a step back. The goals of this activity is for you to understand how the Visionaire algorithm works, for you to understand why simple frequency analysis doesn't work in this. So if you tried that to figure out what my message was, that would not have been a very wise choice. Frequency analysis does not work on the Visionaire Cipher. And the last thing is to just figure out what makes a good versus a bad secret key, aka password. This slide shows you the same things that was right here. So if you want some direction and you're not looking to break my ciphertext or accept my challenge, that's fine. So as long as you do these things, and here's some examples to guide you. You can pause and read them yourself. For me, I am done today. Choose the IB profile attribute that you think fits with today's lesson. And then your DOL to wrap everything up. Tell me what makes the Visionaire Cipher strong, and do so using at least 2 details.